Pascal's triangle is genuinely underrated. It is extremely powerful and useful and so cool. I'm going to show you 15 amazing properties of Pascal's triangle. Now, constructing Pascal's triangle is very easy. All you need to do is start out with a single 1 and an infinite void of zeros to the left and right. And the rule is that the top two numbers add together to create the bottom number. So 0 plus 1 is 1 on both sides. Then again, there is a void of zeros on the left and right. So 0 plus 1 is 1 again, and 1 plus 1 is 2. And you continue on like this. Furthermore, we say that the very topmost tip of the Pascal's triangle is the 0th row, and the leftmost element of a row is the 0th element in that row. The first property is trivial. It's symmetrical. Yes, I know, that is boring. It's obvious. But it does mean that you only need to calculate 1/2 so that you can mirror it on the other side. The second property is what I like to call the hockey stick property. You can choose a diagonal and then make a bend anywhere you want. And the number after the bend will equal the sum of all the numbers before the bend. Did you forget what the powers of 2 are? No problem. You can calculate them very easily just by adding up the elements in the rows. This next property is what Pascal's triangle is known for. The elements in row n represent the coefficients for a binomial expansion of a plus b to the power of n. Here you can see it with 3. Pascal's triangle also has the combinatorial property in that it has all of the numbers of n choose k, where n is the row and k is the element of that row. But the thing is, these two things, the coefficients of the binomial expansion and the combinatorial property, are the same property, because you can write a plus b to the power of 3 as a plus b 3 times. And if you know how to multiply brackets, you know that you need to take one element from each bracket. So if I want to ask, okay, how many pairs of a squared times b there are, that's the same as me asking 3 choose 1, 1 being 1 times b, which is also found as the coefficients of the binomial expansion. For the next property, we will look at the diagonal of the second row. This row alone has so many interesting properties, so keep that in mind. This diagonal contains the triangular numbers. Basically, how many objects you need to construct a 2D triangle with a side length of 1, 2, 3, and so on. As you can see, if I want to construct a triangle with side length 1, I need 1 object. If I want to construct a triangle with the side length of 2, I need 3 objects, and then 6 objects, and then 10 objects, and so on. The diagonal below this diagonal contains all tetrahedral numbers. So the amount of objects you need to construct a 3-dimensional tetrahedron. As you can see, to make a tetrahedron with a side length of 2, I need 4 objects. Let's return to our special diagonal. 0 plus 1 is 1, 1 plus 3 is 4, 3 plus 6 is 9. 6 plus 10 is 16. Yes, that's right. All of the square numbers are in this diagonal. Why does this work? It's because the square numbers are in what I like to call a layered sequence. This layered sequence has 2 layers, and the second layer is constant. You see plus 2, plus 2, plus 2, plus 2, and so on. And if you look at the diagonal above, you can see that when we move down by 1, we actually increase the sum by 2 each time. And since the diagonal below is only affected by the diagonal above, this in turn means that we can get the first layer of that layered sequence, and thus all the square numbers. So now I thought, can we go further? How about cubes? So I tried out, and indeed, the cubes are also in a layered sequence. There are more layers, but it is still a layered sequence. But sadly, there is no diagonal in Pascal's triangle where you can just go down and the amount will constantly be increased by 6. Unless you replace the top one with a 3, but then it's a different Pascal's triangle. This next property is also well known. If you color in all odd numbers and all even numbers different colors, you will approach a very well-known fractal, Sierpinski's Triangle. One more comment about this. I think it is interesting that you construct Sierpinski's triangle from the other way, because when you normally construct Sierpinski's fractal or triangle, you start with the entire largest triangle, and then you cut out smaller and smaller triangles. But with Pascal's triangle, it's like you're starting at the infinitiest, smallest top tip, and then going down and getting bigger and bigger. So Pascal's triangle is sort of already the infinitiest iteration and heading to 0. And without Pascal's triangle, if you were to draw Sierpinski's triangle, you are at the 0th iteration and going to infinity. I mean, that's interesting, right? Another cool property is that you can get powers of any base by choosing any base you want and then constructing a number as follows. And then you will add up all of these numbers and get the powers of the base one above what you have chosen. So as an example, let's choose base 10 because that's what the world uses. If you add up the numbers in this specific way, you will get the powers of 10 plus 1, or 11. Let's go back to combinatorics. Since we know how to calculate n choose k with Pascal's triangle, and also powers of 2, we can calculate the binomial PDF if the probability of success is 1/2. As 1 divided by 2 is the same as 1 minus 1 divided by 2, we can rewrite a few things and get a much simpler formula. 1 over 2 in brackets to the power of n is the same as 1 over 2 to the n. So there you have it. If I'm tossing a coin 5 times and I want to know the probability that I'll get heads 3 times, then I can just look at Pascal's triangle. it's 10 over 32, or 10 over 2 to the power of 5. Another neat property is that the sum of squares in row n equal the middle number of row 2n. As you can see, the properties don't end. They just keep coming. And believe me, the next few properties are going to be amazing. The Fibonacci sequence is also in Pascal's triangle. It's best if you skew Pascal's triangle into a square grid and then add up the diagonals. You will get the Fibonacci sequence, which you can then use to calculate or approximate the golden ratio. If you write Pascal's triangle in mod 2 and then read it in base 2, you'll get all of Fermat's primes. Fermat's primes are prime numbers which can be expressed as 2 to the, in brackets, 2 to the n plus 1, n being a natural number. And the interesting thing is that in these rows, you will only get Fermat's primes and compounds of Fermat's primes. You will never get any other primes. Pascal's triangle also has the Catalan numbers. They come in various problems, like the amount of Deek words for nx and ny, the amount of different ways to connect corners of an entagon, and so on. They are 1, 1, 2, 5, and so on. You can calculate the Catalan numbers by looking at the center column and the column 2 to the right. And you can just subtract the center minus the 1, 2 to the right to get the Catalan numbers. We're back. We're back at this special diagonal. And guess what? We can use the reciprocals of the numbers in this diagonal, which just means 1 over these numbers, and alternate them with plus plus and minus minus to approach pi minus 2. Yup, I guess you could just replace the 1 at the start with a 3 when you're finished. What would it be if there were no pi in an amazing construct like this? Okay, so we've calculated or approached the golden ratio, pi. What other amazing mathematical number is there? E. If you define Sn as the product of all of the elements in one row, and if you take 3 different rows, one next to each other, like this, you can approach E if n gets larger and larger. Of course, there are way more properties of Pascal's triangle. I just don't understand many of them. And I'm sure that we will keep finding more and more properties of Pascal's triangle. I mean, it's infinitely big, and I haven't even gone or started at what happens if you extend Pascal's triangle to the negative side. And there are also other versions of Pascal's triangle where instead of starting with the 1 at the top, you can start with other things at the top.